Welcome. In this part, we will learn about inverse modeling. So to understand inverse modeling, let's revise the modeling step. So the first modeling step, the most important step, is that you define your model purpose because each model has a specific purpose. So that is the first step. Then after you define your model purpose, you develop your conceptual model. And the conceptual model uh, like in hydrology, for example, what we mean by conceptual model, it could be different in different fields, but in hydrology and in water resources engineering, what we generally mean by conceptual model, this is uh, your conceptualization of the problem, including your data, your boundary condition, your conceptualization. For example, if you're talking about groundwater flow and contaminant transport, the geological structure, the mathematical structure. So basically, you put all the relevant information in a way that is amendable to become a mathematical model. So it is not just like you list the processes or you list like relationship between variable, but you put it in a way that is amendable to become mathematical model. Otherwise, that is not like a conceptual model. So a conceptual model is something you can turn to a mathematical model. Then you develop like your mathematical model based on your conceptual model, and then the next step after you develop your mathematical model, you solve the mathematical model. So that's the modeling code. So to solve the mathematical model, you can use off-the-shelf tool like ModFlow, or you can use you develop like your own numerical, you solve it numerically like using solver like MATLAB or Python solver, or you just divide your own numerical method, or you come up with your own numerical method. So that's basically the modeling code. So like you turn, and we have seen in the previous example how to convert like this guy to this guy. Now you have your modeling code. Now you are ready to set up your model and run your model. But when you run your model, guess what? Like this model, whatever results you will be getting from this model will not match with whatever you are observing in the field. And why is that? Because this model is not calibrated. So in model calibration, we basically do history matching. We change the model parameter. That's like one thing you can change. You can change your model parameter until what your model is simulating. So is what you are observing in the field. So let's say this is what you are observing in the field, for example. And now you keep changing the model parameter until like your model, see, that's what your model is simulating, and this is what you are observing in the field until you get this match between what you are observing in the field and what your model is simulating. Yeah. If you didn't get this match between what your model is simulating, you keep changing the model parameter until you get this match. If you didn't get it, what you can do? Well, you can change your conceptual model. So if you you select the calibration targets, you do the model calibration. If you get an if you didn't get like a good match, so let's say here this is the data that I'm observing in the field, yeah. Okay, and then this is the model that I got. So you see here, maybe this is not a good match. It's a good match here because I can match these points, these points, this point. But here, see, I have an overshooting. Like this is what I'm observing in the field. This is what my model is producing. So you get like a big error between these two. So if you don't have a good match, you can keep continuing playing with your model parameter until you get this match, or you can change your conceptual model and accordingly change your mathematical model, or use the same mathematical model but just change your conceptual model like your boundary condition, for example, or whatever, and then you repeat the step. Okay, so the model calibration, if your calibration is okay, then you evaluate the calibration, see how good your match is, what error between your model and the real system. If it's acceptable, then you move forward with next modeling steps. And these next modeling steps, that would be like, for example, forecast or management, and so on. Okay, so these would be like the next modeling step. So in this lesson, the main focus is on this part, like step number 5, the model calibration. So you will learn basically in this lesson what we will be learning. We will be learning how to keep adjusting like your model parameter. You can do this manually by trial and error, or you can use an optimization algorithm until you get a good match between what your model is simulating and your real system. So here, this is like an example. For example, so we have like this model. This is a groundwater flow model for a city. And what we do, we adjust the model parameters. We have some model parameter, like our model parameter here is like hydraulic conductivity K, and anisotropy value for this hydraulic conductivity. So that would be like anisotropy in like XX, for example, for this hydraulic conductivity. Two boundary condition, we have like one boundary condition here is unknown and one boundary condition here is unknown. Uh, uh, Two boundary condition parameter, twofold conductance value. Like here, see, this is one part of the aquifer, and this is a fault here, and then there is a fault here. So the conductance along this fold and the conductance along this fold, these are unknown, like how water flow from here to here and from here to here. So we have like this is your boundary condition. And what is your calibration parameter? Calibration parameter is hydraulic head. I want to simulate the hydraulic head. So you see like the blue line, this is what the model is simulating. The black dot, this is what I'm observing in the field. So you adjust the model parameter. These are my model parameters. So I keep it changing the value of hydraulic conductivity. I keep it changing the value for this boundary. I keep it changing the hydraulic conductance until I get a good match between what my model is simulating, like this guy, and what I'm observing in the field, like this black guy. Okay, so between observation data and model simulation. Yeah. And here, what is the main, uh, my calibration target is the hydraulic head. Okay. That's the state variable. Remember, like my equation is delta H over delta T, so that is my calibration target. So this is what my model is simulating, the head that my model is simulating here, and then I compare it with the heads that I'm observing in the field. Okay, so here, uh, this is more information, for example, about this model. So you see this model here, it has each cell, like each of these cells is 200 meter by 200 meters. That's like the size of these cells. Remember, we like in the previous example, like we had a model that has only 5 cell, and each cell was 3 meter. Here, each cell is 200 meter. Here's the number of cell is about like 400,000 cell. Like in the previous model, we only had 5 cells, like H here, and H here. Here we have like, this is a real life example. So here we have like 400,000 cells. And then these are some pumping well. We have 17 observation wells. So we have 17 observation point where we are observing the data that the model is simulating. The calibration period is from 1975 to 2014, and we have 6 model parameters. So what you can see here in this figure, for example, like you see this pumping well here, WR West Baton Rouge 102 B, which is like this guy here. So you see like this guy here. So like I have data for this guy from about 1980 to 2014 or whatever. And you see like my model like is a perfect fit between what I'm observing in the field and what my model is simulating. And this is not surprising because this is at the boundary here. So if my boundary condition is I probably like set this boundary condition based on the head of this guy, and that's why you find a good fit here. See this guy here, waste Baton Rouge number 50, which is this guy here. So this is the Mississippi River. So you see, like this guy here, you have some good matching here. So at like the beginning here, like you have some good matching, but here you don't have good matching between what your model is simulating and what you are observing in the field. Like you have a underestimation, particularly here at this time. Here you have a good matching, here you have a good matching, here you have a good match. So basically, like that's the idea of model calibration is I keep, like I have this 6 parameter, I keep changing this 6 parameter either by trial and error or using an optimization method until I could get the good match between what my model is simulating and what I'm observing at different observation points. So in this lesson, we will learn how to come up with an objective function so as I can quantify the error to make sure that I want to minimize the error. So here is a fitting error between what I'm observing in the field and what my model is simulating is only 5%. That's an excellent error. Like this means that this is a very good model. It's represent like actual very good representation for the field condition because it is and you can see it, you can visually see it, like how your model, like whatever head I am observing in the field, my model can just present this. So now the flow, the transport, all the process that will be simulated by this model is expected to represent field condition with an error of about like 5%. Yeah. Okay. Of course, this model was calibrated on a high performance computer because this model, like a single model run, takes several hours. And to calibrate this model, remember like how to calibrate the model, you keep changing these parameters. And then you run your model, like you change your parameter, you run your model, you change your parameter, you run your model, like you change your parameter, you calculate the error, and then you run your model, and so on. So depending, like if you are using a derivative-based methods, it will take maybe tens or hundreds of model run. If you are using a non-derivative based method like stochastic method, like the ones that I use here, that will take hundreds or even thousands of runs. And but it can ensure like a better match, a better calibration result. So to do this, I had to do this on high performance computing where you will be running, like it took 3 days to calibrate this model using hundreds of processors like CPUs, like hundreds of CPUs, and 3 days to calibrate this model to get this match because the single model run is several hours. Yeah. But I'm not like for the example I will show you. I will just show you a model that takes a fraction of a second to run, so that we can basically achieve the same results, but the model run, the forward runtime for the model will not be an issue. Okay. So here again, this is model calibration. Like, so you can do this with trial and error. This is the data that you are observed in the field. You design your model, your boundary condition, your geometry, your conductivity field, your recharge, if that's a groundwater model, and then the model will have a certain output. Then you compare the data that you are observing in the field with this output that your model is preserving. Like if you compare this output here, like this part of, if the data is doing good, this part is doing good here. I have a little bit of underestimation, like I'm not capturing these 2 points accurately. But overall, I'm getting the trend. So overall, like my model is getting this trend. So overall, it's doing good. Yeah. One thing, intelligent mechanism for model adjustment. So one thing, I can adjust this model parameters manually. Like I could adjust this boundary manually. I could adjust this hydraulic conductivity value manually. I could adjust recharge manually uh, until like I get a better match between what my model is simulating and what I'm observing. Another way is that instead of using this manually, you use a calibration, an automatic calibration method like best or Unicode. So these are derivative based method. They use something called Gauss-Newton method. So Gauss-Newton method, that's, remember, like that's similar to the derivative test that you used to do, but it calculate derivatives not like using calculus laws, but numerically. So basically, this is how you can calculate. This is a derivative based method, but you calculate the derivatives numerically. not with the laws of calculus. So you can use like these codes and like how to again like this class we don't you like if you want to learn how to use these codes to calibrate a model like we do this in another class. This is called groundwater hydrology class. That's where you will basically like you will have this data, you will develop the model, you will run the model, and then you will use best actually like this is the codes that we use in the groundwater hydrology class. You will use best to calibrate this model and get a good match between your model and the field condition. But now here this is not like here like in this course we don't learn how to use software. This is not the objective of this course. In this course we learn basic concept like how these software work. Yeah, not like how to use the software, but the basic concept and the mathematical concepts behind this software. That's the objective of this course. Yeah. Uh, so now how could I compare? Now that's my question. How could I compare between my model, like what my model is simulation and the data, and to calculate like the error, like I have an error of like 5%, for example, or 10%, or whatever percent. Like how could I calculate like this error, like the match, like if the match between my model and the data? So one way, like this is we call this like the residual. Like so, the goodness of the fit, like how good is your fit, like how good my model is simulating the field condition. We call this the goodness of the fit, and that's basically based on residual. And residual simply, let me show you what residual is. So from here to here, like this distance from here to here, that's the residual. Here the residual is almost like zero. Here I have a big residual. Here I have like this is the residual. Here the residual is like very small, like very small. Here also like very small. So where is my largest residual? Here for this guy. That's my largest residual. So the residual is the difference between the observation and the simulation. So here, this is where what I'm observing, and at the same like space x. So this here could be like x, y, z, and t. So at the same like cell, and at the same time, I see like how much my model is producing. So let's say if this is like 50, and here this point here is like 10, so the residual at this point would be like 15 minus 10, that's like 5. Yeah, so that's the residual at this point. I mean, what would be like the residual at this point here? I mean, the residual at this point would be very small, maybe like zero point 0.1. Yeah, what would be the residual here at this point? So again, like how you compare it, like so you see this point here, oops, this point here, and like the difference between this point and this point, that could be whatever, 1 or 2 or something like this. Okay, so basically you calculate like the residual between your model simulation, like this point here, and your observation. Your model simulation, this point here, this point here, this point, oops, this point here, this point here, and your observation. Yeah. So by making this comparison, you calculate your residual. But and then I want to not find the residual for each point. I want to find the total error. So the total error basically this is something called like root mean square error, and this is just what it is. So like you get like your residual, you subtract them, and then you square them. Why do you square them? Because you will sum them. So if you have like squaring them is very important, because let's say if like the residual here between this is like plus 5, for example. Yeah. And like the residual here is because this is below this is like minus 3. So if you added these two, then the error will be 2. Yeah, because 5 plus minus 3, 2. So basically, but actually your error shouldn't be 2. Your error should be 8 because you have 3 and 5. So, and that's why we square them and then we take the square root again. Because when you square them, you get rid of the negative sign and then you can basically add them. Yeah. So like, so you get like this difference. So that is like 5. Yeah. So that would be 5 squared, and that is here minus 3. So that's like minus 3, sorry, minus 3, like you square it. And in that case, so that would be like 25 plus 9, because like the square, like that would be 25 here, that would be 9. Yeah, that would be 9. And then like you add these guys, so that would be like 36. Yeah, because you sum, like you square it, and then like after you square it, you take like the square root, so that like you square it, so that would be 5. You square it, that would be 9, and then if you take the square root, then you'll be 3. Okay, and then you sum them, and then you divide by their number because you want root mean square error. So if you did this, you will get like the average error, yeah, for all these guys, yeah. So that is like one way of doing this. Like you can use root mean square error. Another way is sum of the residual, sum of the squared residual. You can just square them and sum them without taking the square root. This one will basically, like if you have this one, will treat all points as equal. Like all points will be giving like an equal weight, while this guy here, point with big residual, will have a higher weight because that's the, so that's like a little bit more aggressive. Or you can just do sum of squared weighted residual. So you can, that's like similar to this one, but you assign for each point here weight based on the importance of this point. So let's say, for example, like I only care about the beginning of the simulation. These are like the points that I care more about rather than this point. So here, so for this one, I could assign for this like a big weight. So let's say I have 1, 2, 3. These 3 points I assign for this like maybe 20%, and for this guy like 20%, and for this guy maybe 20%, and this guy might have like less weight, so I assign for the weight of this guy might be, so see this guy's like has 60%, and maybe this guy I only assign for him like 10% only weight, 10% weight only. So and then this guy would be like 20% again. Yeah. So here, like that is this weight. Like basically, I'm telling him when you do, like when you are doing this optimization, I care more what I want you to match. Like keep changing the parameter, and I want you to match. These points are more important for me to match than like these 2 points at the end. So that's why like you assign this weight, or you change this weight. Okay. And again, you solve this as an optimization problem. Remember, like when we solve it an optimization problem, like you, like your objective function looks something like this, and you're trying to find like the minimum error. So in that case, for example, if that's my objective function, so the minimum error will be here. Yeah, that would be like the, so that's f of x, and that is x. So your minimum error, that would be the minimum error. But in real life problem, it's not one parameter. It's like, so here, this is f of x. In real life problem, like in this problem, for example, here, I don't have only one parameter. I have 6 model parameters. So this is a 6-dimension problem. So this is for a 2-dimension problem, like this guy here. So the minimum function here would be here. So that would be the minimum value. That's in 2D. In 3D, I cannot draw it. But like, for example, like that problem, that previous problem, your objective function was a function of 6 parameter, but for 2 parameter. But that's the idea. Like you follow like derivatives, and like if you calculated derivatives, you will keep going here until like you reach this point. That would be like your minimum point. Like you calculate gradient, yeah. Remember, like gradient descent. So for 2 parameter, it would look something like this. And basically that is so you start like from an initial value, and so and you calculate like derivatives numerically. So you calculate gradient. So from here, this point will take me to here, then I calculate gradient from this point will take me to here. I will calculate gradient, this point will take me maybe to here, and then to here. If I started from here and I calculated gradients, this gradient will take me from here to here to here to here to here until I reach this point, which is my minimum point, or in that case, like maximum point. No, actually, in this case, is a minimum because this is, yeah. So I reach the minimum point, which is around like 1000, or here even like, yeah, whatever this minimum point is. Yeah. And so if I started, for example, yeah, so basically you just like calculate gradient. Like if I started from here, I might go from here to here, and then from here to here, and then from here to here. Yeah. Okay. So your initial point will affect the solutions. This is a derivative-based method. That's why we use a stochastic-based method, because the impact of the initial point could be like not as big as the derivative-based point. Okay. So let's do an. So this is just like an introduction. Let's do an actual problem. Yeah. So this is just an introduction. Uh, let's do an actual problem, like define the model purpose, do the conceptual model, see the mathematical model, and do a calibration exercise. So that's basically would be our next step. So the model purpose, step number one, defines the model purpose, estimates the hydraulic conductivity and storativity of a formation. So I want to estimate K and S for a formation. Regardless, I mean, this is not a groundwater hydrology class. You can, if you don't understand what are these two, that's not important. The most important thing is that you see the calibration step. So, so step two, conceptual model for transient flow to a well. So I create a conceptual model. So here is my conceptual model. So here I have like the pumping. So like to do this, I will like how to estimate K and T. I will keep pumping water, and this is my initial hydraulic head. You see here, this is my initial hydraulic head. And once I pump water, what do you think will happen? Like my hydraulic head will decline. So after some time, it would look something like this, and then after some time it would more time it would make it like after very short time, like so this is my initial head. Yeah, after very short time you will find a decline like this. Yeah, and that's basically what we are measuring here. So after 3 minutes, like I have like 3 feet of decline at a distance of where like this is where I'm observing this. So at R1, like at this distance, let's say an R1 of 8 points, so at a distance of 8.24 meter, after 3 minutes, let's say like after 3 minutes, I have like this small decline here, which is only like 3.3 feet, yeah, 0.3 feet. And then after 5 meter, I will have zero point 0.7, so that would be here. And so on. After, let's say, 20 meter, it will be this much. Yeah. So basically, I'm pumping out at a constant rate, and I am observing how my head is dropping at a distance of 4.25. And this is basically the data that I'm collecting from the field. So in the field, somebody will be pumping from here, or a pump will be here, and somebody will be standing here, or you have an automatic logger here that will keep recording the drawdown, like how your head is dropping down with time, with different time. Yeah. So that is basically my conceptual model. You define the aquifer thickness. So the aquifer thickness here is giving like this B is giving as like 48. This distance here is giving as 4 like feet. The total pumping time from the beginning to the end of the experiment is like 500 like minute. This is giving Q, like the Q here, like the pumping rate here is giving as 20 gallon per minute. Yeah, so you need to convert this to gallon to feet. Yeah, and then I'm asking you to find like transmissivity in like feet square per day. and the storativity, which is unitless. So again, I need to convert like gallon. Uh, I need to convert this time from minute to day, and I need to convert this gallon per minute to like feet cube per day. Yeah, so that my unit will be consistent. So that's basically like my conceptual model. This is a mathematical model for doing this. So you can think of this as like your head is changing in x and y direction, because like this is like once you start pumping, it will this is how it will evolve in time. You have like these circles that is in time. So this is like a top view. If you have like a top view, that would be how the head will be like dropping down in time. So you can take advantage of this, and instead of like using a Cartesian coordinate, you can use like a radial. Uh, you can use this radial coordinate. Okay, instead of a Cartesian coordinate. You define your initial condition, you define your boundary condition. So this is basically your boundary condition, and this problem will take this form. And you remember this form? Does this look familiar? Yes, this is basically the this equation. We know it has an infinite series solution because this is called like a integral function in the exponential form, exponent integral. This is what's called like an exponent integral. And if I define u as this, then this guy will have a solution. So you define your mathematical model, and then uh, your mathematical model, you try to solve it. And we know that like this guy will have this type of solution where like this guy here, this is the solution of this guy, and EU is equal to something like this. And we did this example before. Yeah. Uh, so we know this. So now here is my model setup. Basically, I have this is my equations, and my main equation like drawdown, like here, like this is the drawdown as a function, which is a function of q and t and WU, and WU, this is a function of like S R, like this is the distance from where I am observing the transmissivity. That's what I want to estimate, and the difference time step. So and you know how to do this. You did this before in the previous example. Yeah. So basically, this is my model, and can I solve this? Yes, can I solve this? So to solve this, basically, like what I want to do, this is my model parameters, the t and the s. So the objective here, like see, this is my t and drawdown. So let me draw this, for example. So this is like the different data points that I have here. I'll just draw them roughly, yeah. So these are like the different data points. So here, this is S observed, and this is T, like the TI, a different time step. And if I plotted this model, it would look something like this, yeah. But this is not a good fit because like you see the model, so if I plotted like S, so this is what I'm observing in the field. I can also plot S as a function of t. So I can put any s, like I can assume a value for this guy, because like here, what do we know and what we don't know? So we know q, we know this guy, we know this guy, this is unknown. And like with respect to this guy, we know the r, we know the 4, we know the t. This guy is unknown and this guy is unknown. So I can just put any value for s and t and plot my model, yeah? But if I did this, my model will not match with what I'm observing in the field. So how can I make my model match with what I'm observing in the field? I keep changing the value of this guy and this guy until like this guy match this guy. But how would I know that this guy is matching this guy? I can see it visually, but better than seeing visually, you can calculate uh, your objective function. So the objective function that I will use here is that I will use sum of a squared residual. So this is called like least square regression. So sum of squared residuals, this means that the difference between like what I'm observing in the field, like remember this is the residual, I will take like this distance, square it. So this is the residual, I will square it, and then I will like see this is the residual, the residual, the residual, the residual. I will like square all these and sum them up. So that is called like the sum of the squared residual. And if I did this, this is like the good mesh that I got basically. So let's do it. So let's it's better to do it, and then once you do it, you will get a better understanding. Okay. So here, I don't know if you how much you can see from here, but let me. Okay. Okay. Let's see here. Or let's first look at our model. Yeah. So this is a different time step. Yeah. This is a different time step in minute. I'm changing this to day, and then here is what I observed in the field. Yeah. And based on what I observed in the field, I can just plot this data. Yeah. So this is what I did here. So like this blue dots here is like t versus s. So like this point, for example, would be this point here. This point would be like this point here, and so on and so forth. So this is my observation. Now I have a model for this. So my model is that for my model, I have S as a function of Q, T, and WU. And to calculate W, I first need to calculate the U. So I can just calculate the U by just putting this equation, like R squared over S over T over blah, blah, blah. Yeah, that is basically. And then once I know U, I can substitute U here in this equation. Then I can calculate like the WU. And then once I know W, I can substitute W in this equation, and then I can calculate like the drawdown, my model. Okay, so that would be this point here. And here, like I don't have any observation here, so there's no residual here. So here, basically, this is what my model is, and this is what I'm observing, and the residual will be like this guy minus this guy and the square, and you square it. Yeah. So that would be the residual at this point, at this point, at this point, at this point. That would be like here, for example. That would be the residual here at this point, like the difference between this guy and this guy. And then what you can do after you calculate the residual, we can do the sum of the residual, because that's my objective function. My objective function is what I'm observing and what I'm simulating squared, and then you sum them, and then so and my problem here, I want to solve an optimization problem to minimize this. Minimize this means that I want to minimize this sum of residual, which will in uh, which will reduce the difference between what my model is simulating and what I'm observing in the field. So here you have a good match because I already did this optimization problem, but typically you don't know these values in advance because like this value is unknown and this value is unknown. So you can do it by trial and error. So let's do this by trial and error. Maybe so like I just showed you the solution, but typically you don't know the solution in advance. So I can just play with this guy by trial and error. So like I will say my transmissivity is here and this guy is equal to. So now you see my residual now is increasing. Like see the residual here is very large. The sum of the residual now is like 2000, like huge residual. Then you say, okay, I mean, that's not a good residual. Let me make this a little bit smaller. I don't know if you can see here. That's not a good residual. That's 2000. So I will say maybe let me do this, make this 1000 and make this like e to the power negative 25. Oh, the residual now improved dramatically. It is like 47, and now you see here this also improved. You said, okay, now let me change this to this value. Oh, now it's 6. Oh, wow. Now it's even better. Like, see the residual improve. Now this fit looks very good. I would say maybe I'll play with this guy. I will put 10 to the power minus. Oh, now this is not good. So I will say e 10 to the power minus 4. Oh, that's even not good. So I will say like 1 e to the power minus 5. So you see, like, you keep playing with this like manually, like with trial and error. Yeah, this is not good. Yeah. Let's say 1 to the e to the power minus 5. Not good. 1 e to the power minus 4. uh, 2 e to the power minus 5. Yeah, see, something like this. See, now the residual is very good. So you see, you can do this by trial and error, or you can do this automatically using, like, instead of you doing this with trial and error, you run an optimization algorithm. And how to run this optimization algorithm, let me show you. Like, so you can come here, like Excel can do this for you. You can go to get add-ins, and then uh, once you go to these, ooh, this new Excel look different. So let's, oh, okay, I think you can go to options. Yeah, you go to options, add-ins. Okay, so let me show you this again. So in Excel here, like, you go to options, you go options here, and then you go to add-ins, and then you do which one? Solver add-in. Okay, so you click on this guy, and you click go, and then you will get here this list. So you can add all of them, but you can analysis tool pack, and so you add like this solver add-in, then you click OK. So once you clicked OK, then I think you will, when you get to data, like, you go to data, and you see here you have this solver. Okay. And in this solver, basically what you will do, you will define an optimization problem. So set the objective. So now what do I want to do? Like, I want this guy to minimize it, like find the minimum possible value for this guy. So that's an optimization problem by changing what? This is my decision variable, like this guy and this guy. This is the guys that I was playing with. Subject to, now I want to add a constraint, like, so let me, because let me just delete this guy. So, like, I want by changing, like, so here, let me do this again. So you come here to, like, data, go to solver, this is my objective. I want to minimize this guy by changing, like, these two guys. Yeah. Subject to, I want to add a constraint. I want, like, this two guy to be larger than or equal 0, because I don't want to have negative. Yeah, I don't want these guys to be negative, so I want this guy to be always positive. So that is my and then you tell him solve, and then, well, if you told him solve, it will basically tells you now, keep the solver solution, restored original value, and it will show you, like, create a type of, specify the place of sheet on the work. So here, this is like if you need a report, uh, or you don't, like, in that case, you can just don't. But uh, but the idea is, see here, we got a perfect match. So the optimal solution for this, or like the solutions that will make a perfect fit between your model and your observation data, is this value, like here, 1928 and 2.175. And you see here a perfect match. So now this model, I was able to calibrate this model basically to get a good match between what my model is simulating and what I'm observing in the field. And this gives me a value of transmissivity is equal to this value, and the storativity is equal to this value. And this is basically what I need to, that's the purpose of this model, is that I want to estimate, like, these two value. And how do I estimate these two value? I just find the value of t and the value of s that makes a good match between my model and what I'm observing in the field. Okay, so you can practice with this. Like I have here homework problem. So for this homework problem, basically, like you can. Oh, here they tell you some uh, uh, like so the engine, like they use like a non-linear solver. They tell you like how many iteration did it reach and so on, and the sum of the square residual. So the original values, the final value, like you see, like your sum of the square residual, very small. Remember, we started with something that's 100 or whatever. See the sum of the square, because like you see the difference between what I am observing and what my model is simulating is very small. So try to do this. Here is another example. So this is like if you want to learn more how to use this solver for optimization, not an inverse problem, but another example, like you can check also this YouTube video, but try to play with it. Like this is your homework problem. It is the same problem. So basically what you will do, you can use this, like you can copy and paste this value like here, and make sure that you also change your time from minute to day, and put like your Q here. See here, I'm converting the Q from feet to feet cube per day. So make sure that like the unit is consistent. I'm putting the R here in the unit in feet. So make sure that the unit is consistent. So you can try solving this problem. That's a good exercise for you. And that's all for this lesson. And like see you in the next lesson. So basically, like to solve this problem, like you need to know how to use Excel. Yeah. If you don't know how to use Excel, you just like learned. Yeah. So try. You can check like using this video, and this video has a series of other videos that also teach you how to use Excel. Yeah. Okay. So that's all for this video.